So, in last class we started talking about MDL, right. So, this is for estimating the generalization error of a classification model. Okay. So, here as I said in the last class, so there are two guys apart from each other. So, A is having the information of the class level of the each object, and B guy he wants to know the class level of the A. So, in that case what A should do, A will make a decision tree out of the training set he has, and then he will transfer that decision tree to the guy B. It is not sufficient, as I said, because as we know there is something called the training error. Decision tree always may not give the training error 0. So, therefore, he has to also send the information for which object this decision tree will make mistakes. Okay. So, therefore, there are two terms. So, this is the term for what is the cost. What is the cost means actually how many bits needs to be transferred for the decision tree. So, decision tree means how many leaf node and what is the split conditions and so on, how many internal node and so on. And this is something what I said is the training error information needs to be sent, and since it is a binary class problem. So, if there is a mistake means actually result will be just flip of the wrong results. Okay. So, then it will be the right one. So, therefore, let us say if the guy he send is x 3 giving wrong result by the decision tree, that means x 3 actually giving results 1. So, he will trace this one, that is the B guy, he will trace the decision tree for x 3 and he will get the result is actually 1, but then he will flip it 1 to 0. Okay. So, that is we discussed in the last class, and then we have a problem here. Let us study this problem and I will give hints how to solve this type of problem. So, compute the total description length of the decision tree given in this figure here. Okay. The decision tree is obtained from a training set with 4 binary attributes and 3 classes. Okay. It has 100 records. The decision tree wrongly classifies for 9 cases. Consider the following scenario. What is that following scenario? So, that is we discussed that there are two terms for computing the MDL. One term is what is the complexity of the decision tree. Okay. So, how do you compute the complexity of the decision tree? This is the hints. Each internal node is encoded by the ID of the splitting attribute. So, they have simplified the problem just for complexity of the decision tree means each internal node is encoded by the ID of the splitting attribute. So, how many attributes are there? 4 binary attributes are there. Okay. So, then how many bits do you need to represent each attribute? So, there are 4. So, then you need 2 bits. So, for each attribute you need 2 bits. Okay. And then each internal node is encoded by the ID of the splitting attributes, that is all, only you represent the ID. So, how many internal node you have? 1, 2, 3, 4 internal nodes. So, then you need 4 into 2 for the first part, that is A here. Each internal node is encoded by the ID of the splitting attribute. So, splitting attribute, so there may be a split on based on some attribute. So, then ID what will be the ID of attribute starting from 0 0 to 0 1 1 0 1 1. So, any cases you need always the ID. Okay. So, that means 2 bits. So, 4 into 2. Each leaf node is encoded by the ID of the class it is associated with. So, how many leaf node you have? 1 2 3 4 5 leaf node, and then how many bit do you need? There are number of classes 3 classes means you need how many bit you need? Log 3 base 2. Okay. So, these mean this number of bits and then 1 2 3 4 5. So, this is the complexity for what is called the cost of the model. The MDL principle, it has two terms, one is the cost of the model and alpha you consider is 1. So, if you move back little here, so alpha into cost model, so you got the decision tree model cost. Is it okay? And next another thing is here is the ID, the decision tree wrongly classifies for 9 cases. That means 9 objects information needs to be sent. Okay. So, 9 objects means how many objects are there? 100 records. For each record can be represented or record index you have to send only, okay, no other information. So, then record index means 100 records. So, then how many bit do you need? Log 100. Okay. So, 7 bit approx, right, 7 bit, and here this is 2 bit here. So, that is not sufficient, you have to send the class level also. So, this is for the binary classification problem, this is sufficient for the one index, but this is not. Then how many you have to send? 9. It is not sufficient. Along with that, what you have to do it? You have to send the class level. So, class, because earlier it was binary class, so simply it could be flipped, but here you have to send the actual class level. So, for the 9 along with the decision tree, he will send the 9 objects with their actual class level. That means, indirectly this decision tree is making mistakes on 9 objects, okay, on the training sample. So, therefore, you have to add also the class level. Class level you have this one. Okay. So, then this will be 2. So, this will be the total cost for sending the information from A to B with this simplified assumption. Now, question is how to handle the model overfitting. So, this is the problem for the model overfitting, right. So, there are 2 cases, one is pre-pruning, another is the post-pruning. Okay. So, what is pre-pruning? So, you stop if the number of instances is less than the some user specified threshold, or you stop expanding the current node if the gain in the impurity exceed a pre-specified threshold. So, there are 2 ways. So, before estimating how long that tree can grow, so you stop in between, so that complexity should not be so high of the tree. That means, number of nodes should not grow in huge number, but this is hardly used in pre-pruning strategy, it is not used actually. Other way around is the post-pruning strategy. What is post-pruning strategy is you allow the tree to grow, and what you do it, you estimate the generalization error after removing one subtree, and if it is giving better results after removing, then you trim that particular subtree. Otherwise, again you go to the subtree and again you expand it. Okay. So, here example is like that. Earlier we saw some examples, say suppose this is the tree and you expand into 2 or 3, whatever it is. Now, you estimate the generalization error if there is no subtree. What will be the generalization error if there is no subtree, and you estimate the generalization including this true subtree. If you find that after forming the subtree there is no gain is that is the generalization error is not decreasing, that means it is increasing, then what you do it, you remove this subtree and you keep this is as a leaf node. As I said in a class that what will be the, whenever we are talking about leaf node, so you have to say the class level. What will be the class level? Class level will be the majority of the pattern belongs to which class, so that will be the class level. Okay. So, replace a subtree by a leaf node if the generalization error improves. That means, if the generalization error after putting the subtree, if the generalization error increase, then you remove this tree, this subtree. And how to use the MDL principle for estimating the generalization error. As I said, the class level of the leaf node is determined from the majority class of instances in the subtree. So, majority of the objects belongs to which class? So, that will be the class level of this leaf node. Okay. So, this is the same thing here, same thing is written here. So, we follow the postponing strategy, because then only we will be knowing how far the tree can be, whether we will first expand it and then we will try to see the what is the generalization ability of the tree. If the generalization ability is more, then we will keep on expanding, otherwise we stop at this at the particular point if there is no improvement of the generalization error. So, here we go. So, let us say we have a set A, here we have a class 20 and class 10. So, what will be the error? So, majority of the pattern belongs to which category, that is yes. So, error will be 10 by 30. So, that is the training error before splitting is 10 by 30. So, what will be the pessimistic error? So, that is the formula we use, that is the error rate plus how many leaf node? This is 1 into 0.5. If you move back, you can see the what is the pessimistic error, that is the training error plus alpha here is taking 0.5 into leaf node, number of leaf node by size of the training data set. So, that is why we get this value. Now, if you split into A1, A2, A3, 4 subtree. So, this will form a leaf node, this will form another leaf node, this will form another leaf node, and so on. Now, we count what will be the error if you have a 4 leaf node. So, this is what will be the class level, that is the class level will be 8. So, error will be 4, here error will be 3, here error will be 1 and here error will be 1. So, 4 plus 3 7, 8, 9. So, error will be 9, but how many leaf node? Leaf node is 4. So, error will be 9. So, that is the training error will be 9 by 30 plus how many leaf node? 1, 2, 3, 4, 4 leaf node. So, 0.5 into 4 by 30. So, you will get it 11 by 30. So, after splitting you see this is the error here, and before splitting error was 10.5. So, therefore, this we should not, this should be replaced by the 1 leaf node. So, if you replace this one, all values yes, 8 plus 3 plus 4 plus 5, okay. And here is, so you will get automatically you will get the class no 10 and majority class is 20. So, therefore, here class level will be yes. So, here we check with the specific error, but same thing you can do with MDL principle. Okay. So, MDL principle is what? This is there is on a single node. So, then how do you represent this split? So, earlier example you have seen that each split is represented by the feature ID or attribute ID. Attribute IDs, there are binary attributes, there are 4 attributes. So, therefore, each attribute will take 2 bits. Similarly, you can compute here with MDL principle, and if you can show that after splitting there is no gain. So, we obviously will replace this subtree by the leaf node. Okay. So, now we have to say we learn the classification technique, at least one classification technique, that is decision tree in details. Now, what we have to do? We have to evaluate the classifier. That means, whenever we build a classifier, we have to evaluate the classifier, whether classifier is good or bad, whether what is the performance of the classifier. So, therefore, we should know how to evaluate a classifier. Okay. So, there are some term is there. So, what you do it? So, you have a data set, that data set will partition into two part. One is something called the training data set, another is called testing data set. For the training data set, we using training data set we will make the model, and testing data set we will verify the performance of the classifier. Okay. And what you do it? This is something called holdout. So, suppose you have a data set, so you make 80% is training data set and 20% is the test. So, this is one time. Again same data set, what you do it? Again you make 80% random, 80% and 20%. So, you make different training set with different holdout percent, the repeated holdout you take it. That means, you do always 80-20%, but 80% training set always not the same set of objects, it is not the same set of objects. It is 80% of the total data, but not the same set of objects, because you are taking again you randomly you are choosing again 80% of the data. So, you will get the different set of objects, okay, and then you sum up the results. Another is something called the cross validation. So, cross validation is something you use for parameter setting. So, what is done is cross validation. I will tell you, when we will find a parameter in a classifier is something called the k nearest neighbor classifier. So, there I will detail what is the usefulness of the cross validation. So, till now for the evaluation what I said is, if I summarize, for entire data set we will partition into two part, one is training set, another is test set. For training set we will make everything, for what everything means, we will do the model and we will estimate the generalization error everything using only the training set, but not with the test set. So, after model is built, now to verify how much good the model is, then we will use the test set. So, this is the basic idea of the machine learning data mining applications. So, test set you cannot use for the building the model or estimating the parameter, okay. And you do repeatedly the same thing, again another 80% you take and 20% you put at the test set, and then you take the average result. So, that will be the results. Now, we have to see how do you report the results, whether my classifier is good or bad. If I say is out of 100, 49 it is good and 51 it is bad, and so on and other, but we should have a metric to represent, okay, what is the accuracy or what is the value, what is the metric value by which we can judge, okay, this classifier is really working good. Okay. So, that we will see next. This cross validation, as I said, I will tell you later. So, in details for when we will find the some parameter in other classifier. Now, we will concentrate this part, that is something called the confusion matrix. Okay. It is very easy concept, if you never learn earlier, so this is the time to learn, because many of you will be working in machine learning and IDS also. So, everywhere there will be something that is called the confusion matrix, and almost all machine learning algorithm you have to report the results based on the confusion matrix. So, if you learn it is good here, otherwise it will be you eventually you have to learn in some time in future also, but so today you should learn what is the confusion matrix. So, before that, so how do you evaluate whether the classifier is good or bad? Say suppose you have total data is 100 object you have, and then out of 100 object 80% you have used, 80% means 80 objects you have used for the training data set for making the model, and then this is 20% data is like test data set. Okay. So, out of this 20% data, so you count how many objects rightly classified by a classifier, in this example decision tree rightly. Let us say out of 20, all 20 are rightly classified. So, then you count the test record correctly or incorrectly predicted by the classifier. Okay. So, if it is 20, so it is 100%. Okay. So, out of 10, if it is 10%, 10 objects rightly identified, so obviously other 10 is wrongly classified. So, your error rate is also 50% and then accuracy is also 50%. But if a classifier is doing this type of performance, so this is not a good classifier, because a classifier is, will say a classifier is at least better than the random guess. So, if any classifier says 50% accuracy, so always you will get the 50% accuracy without running any classification algorithm. So, that is something called the random classifier. So, your its accuracy is 50%. So, for any classifier you propose in future or you work with any classifier, so that classifier accuracy must be above 50%. So, baseline is 50%. So, any random guess is 50%. So, your classifier should be above 50%. Okay. So, this is the basic thing of the model evaluation. Now, we will go into confusion matrix. Okay. We will invest little time here to understand what is what. So, here is the confusion matrix. So, we talk about the binary classification problem, that means you have two classes, okay, either positive class or 0 class. Now, what you do it, let us say I have a positive class and negative class. So, now I write it here positive, negative without understanding anything, like positive and negative. Now, what you do it, a classifier can say this class is positive, this object class is positive or negative, this is the two possibilities. Okay. So, this is something we will write, if it is a positive, then we will write in this horizontally, that is row wise, and if the classifier says negative, we write on the also the that second row. Got it? What is happening? We have a test data set. So, 20% test data set, you take a pattern, say let us say x81, we identified what is the class level. Okay. So, x81 class level is yes, that means positive. Okay. Similarly, next we talk with x82. What is x82? I consider that there are 100 objects, 80% I use for the training data set. So, rest 20 objects, that is starting from x81 to x100, that is the test data set. So, you take out x81 data set and you verify the class level using the model here decision tree, and I found the class level is positive, that is why I wrote the positive. Similarly, x82 I found the class level is negative, and x83 I found the class level is positive. I means that is the model, we build it. So, then I count how many objects are positive class and how many objects are negative class. That means, it is model is saying how many objects out of 20 objects, model is saying is 12 class is positive class and other 8 class is negative class. So, that is what we do is these 12 objects should be in this row, either it can be here or it can be here. Got my point? So, 12 it should be total 12. So, I do not know where should I keep it, we should keep it here or we should keep, let us say this is one point and this is one. Okay. Whether I should keep on the this position, that is A00 or A01. Okay. So, that is but total, if the positive class, total value should be 12. Now, if it is a negative class, total value should be 8. Okay. Now, you move the next, out of this total positive class set by the classifier, classifier said is 12 objects are positive class. Out of these 12 positive class, you see how many objects are really positive. Really positive means you had the class level when you have the data set. When you had the data set, say here 80, you know the class level here. Here also you know the class level, but you did not use this one for making the model, but you know it, right. Computer does not know or algorithm does not know, only algorithm knows ki this portion, that means he knows the class level, but you have the data where you had the class level, but you did not use that class level for making the model. So, you have that information. Now, you identify these 12 objects here which are predicted as positive class by the decision tree. Now, out of these 12 objects, you see how many are actually positive. That means, classifier predicted as a positive and actually they are positive. Okay. So, let us say out of 12, 8 are positive class, actually they are positive class and classifier also predicted as a positive, and obviously rest will be 4. Similarly, 8. Okay. So, out of these negative classes, he predicted how many are positive, actually positive. Say classifier said is 8 negative class, out of this negative class, how many are actually positive? So, let us say 4. So, then you have to write 4 it here and 8 is here. So, that means it has, if you see on the column wise, so this is the actual class level. Actual class level is there are 12 positive class, you just add it 12 positive class. And another 8 is negative class. Okay. Yeah. So, that is one example I have taken. Okay. So, there are 20 objects in the test data set. Out of the 20 objects, 12 objects is having class level positive and 8 are negative class level. So, this is the reality, this is the actual data. Now, out of the 20 class, out of the 20 objects, classifier does not know the actual class level. So, we ask the classifier, it is like I know the answer, right, but I am asking you the questions and you should answer. So, I know the answer, but you do not know the answer. So, it is very difficult for you to say whether answer is right or wrong. I know the answer, it is the same way. So, I ask, I teach you and then I am just testing you how much you learn it. It is exactly the same way. I made a decision tree, okay, and now I will verify how much decision tree it learned out of the training data set. I know the answer. So, similarly, I know the answer here, I know the answer here. Now, I am giving the object x 81 and you tell the class level. So, he says the class level is positive and he says the next is class level is positive and so on. So, whether this class level is positive, really positive or not, if it is really positive, then we will include it here. If it is a negative, classifier is saying is a positive class, but actually it is negative, then I will add it here. Now, we will move to the second object. If the classifier says is okay, it is a negative class, that means it will come on the row side, second row, but whether I will put it here, whether I will put it here, you have to see. I say or classifier said it is a negative class and actually it is a negative, then I add it here. Okay. Now, if I say classifier says it is a negative class, but actually I say that object's class level is positive, then I will add it here. So, now we keep on adding the each square here is block and then that is the total is here is 8 4 and then 4 4. So, total I had 12 positive class. So, that should be matched, actual class level is 12 and obviously it is 8. So, that should be matched, but here we cannot tally it. It is whatever the classifier, some classifier says, say if you try with other classifier, let us say you learn only the decision tree. If you would have learned some other classifier, let us say x, x may say out of 8, 6 is here, and let us say here this should be, obviously it is 6 means then this should be 6. So, this should be 12, and this is how much, this is 8 means this should be 4. So, this will remain fixed because this is actual, this will not change, this will change. Earlier it was 12, now it is 10 10 because it is a different classifier. Got it? Now, because I have two classifier, which classifier is good, how do you judge it? So, this is something called the accuracy. That means, number of times rightly classified, it is a positive class and it is saying positive class. So, this is plus this one. So, 6 plus 4 divided by total number of object, that is 20. So, that will be the accuracy. So, in earlier case we put it 8. So, 8 plus 4 12 by 20. So, in earlier case classifier was much better than this one. So, what you have to do for the binary classification problem, for other problem we will see little later, it will take some time, but for we concentrate the binary classification problem, okay, and then we identify the what is called is the accuracy. Okay. So, I stop at this point. Okay.